When I say spectral multiplexing, what I really mean is I want to get a lot of spectra all at once, probably by messing with my focal plane. So this sort of technology in the far ultraviolet has been advanced by 2 rockets. I'm going to be talking today about the OAxFORTIS rocket, which is, as I said, a rocket out of Johns Hopkins. The team from the last launch is pictured there, and I am now a part of that team. I am also going to be talking about the INFUSE sounding rocket out of the University of Colorado, which I built as part of my thesis work. These 2 rockets both look at spectral multiplexing in fundamentally different ways, but they have both advanced the field. So I'm going to be talking about those 2 different ways, multi-object spectroscopy and integral field spectroscopy. I'll go into spectral multiplexing in the far ultraviolet, talk about the 2 rockets, and then look to the future. So when you're looking at traditional point source spectroscopy, you're usually looking at 1 spectra per pointing. So you get your aperture, you point it at the sky, the star, the galaxy, whatever you're looking at, and you get 1 spectra out of that. And that example is seen in the blue circle in the right picture. And what that means is if you want to get many objects or multiple points along an extended object, like a galaxy or a supernova remnant, you're going to need to take a lot of telescope time and do a lot of pointings. Another traditional way of doing spectroscopy is long slit spectroscopy, which is that blue rectangle in the right picture, where you put your long slit on the sky, and you can get multiple spectra out of that, but only along that 1 slit. So when you need to, again, look at an extended object, you're stuck doing a push broom method, stacking a lot of those, taking a lot of spectra, stacking them on top of each other, and again, you're taking a lot of telescope time to do that. With multi-object spectroscopy, you mask off certain parts of your focal plane, and you take multiple spectra of multiple objects. So this is most useful if you're looking for, say, a galaxy field or some sort of cluster of stars, where you can put 1 aperture or 1 fiber on each star or galaxy and get a spectra out of that. Integral field spectroscopy works a little bit differently, where you get spectra at every location on your field of view. So that's very useful when you're looking at something like a photodissociation region or a supernova remnant, something that does not have individual objects in it, but is rather 1 extended object that you want to see all along the field. And there are different advantages and disadvantages to both methods, multi-object spectroscopy, and one of the key limiting factors is just detector real estate. How many spectra can you put on your detector? So for a MOS, you might have a very large field of view, but you're only picking out a certain number of spectra in that field of view. For an IFU, you might have a smaller field of view, but you can see everywhere in that field of view. So different science cases work best for each application. Now this is important because Habitable Worlds Observatory has baselined having a MOS as one of its instruments, and there has been a lot of interest in including an IFU either as a sub-instrument on that MOS or as an instrument in its own right. So spectral multiplexing in the FUV is quite difficult. We cannot use transmissive optics, and we cannot use a lot of optics. Transmissive optics kill your far ultraviolet throughput, and reflectivity in mirrors is lower than, say, in the optical, in the far ultraviolet. So that's always a challenge. The way we do multi-object spectroscopy is typically by microshutter arrays. These have been used on JWST, and what they are is just an array of these very small doors, and you pick which door you want to open depending on where your object is, and you get a spectra out of that door. There's a picture of OAxFORTIS down there. You can also use digital micromirror device arrays, which is a very similar principle. You have an array, but instead of being little doors, they're little mirrors, and they can point the spectra at different places on the detector. It gives you a little bit more flexibility. Those have not flown yet, but they will as a ride-along on the next INFUSE launch on the SUMO instrument. And for more details on that, please don't see Alex Houghton's talk. He was going to give a talk, but he is unfortunately unable to be here, and so Celeste is filling in for him. For integral field spectroscopy, we use image slicers. Image slicers are just stacks of thin angled mirrors. Each mirror is angled in a different direction, and you are effectively creating a stack of long slits, carving up your focal plane and making a stack of long slit spectra, and there's a picture of the INFUSE rocket recovery down below. So OAxFORTIS, like I said, we are flying a microshutter, or we are doing multi-object spectroscopy and flying a microshutter array. Now, I mentioned an MSA has already flown on JWST, but just because it's flown on a big mission doesn't mean we can't still be making technology improvements. We are flying on the next flight, the next generation microshutter array. The JWST microshutter array is enabled by this big magnet. It has to go behind the microshutter array. It takes a long time. There's a little bit of risk involved with anything that's moving like that. We are instead going to electrostatic operation only, so it enables a larger format, you can do things faster, and it's a lower risk. And on the right, we have one of our candidate microshutter arrays that may be flown on the next flight. All of the shutters are open. There are some stuck closed shutters. If you've ever seen an image of the JWST microshutter array, you'll be familiar with this. And ignore those two closed rows, that was an electric short. Because we can open whatever microshutters we want, we can only open one per row. That's just in flight, that's just a science restriction. You don't want to be confusing your spectra in flight. But on the ground for testing, we can make it say whatever we want, including the names of our institutions, or if you are my advisor as a graduate student, your name. So a little bit of fun with instruments on the ground. OAxFORTIS launched and successfully observed M10 last August. The next launch is going to be June of 2026. And if you want to see more information about OAxFORTIS and the science results, please see Mackenzie Carlson's poster. It's up in the poster room. So now on to INFUSE, and integral field spectroscopy. INFUSE is enabled by an image slicer. INFUSE was also the first far ultraviolet traditional IFU to ever fly. And INFUSE image slicing is a little bit different. Image slicers are typically used on the ground, and if you've ever seen a picture of, there's a lovely picture of Muse. Muse has something like 30 reflections in the spectrograph, and there's a person standing next to it, and they're just getting swallowed by all of the material. We don't have that room for that many reflections, and we don't have that much room on a sounding rocket. So instead, we got a little bit creative with our optical design, and instead of spending all of our spectra to one grating and then messing with the focal plane later to make everything line up on the detector nice and neat, we sent one slice of the image slicer, 26 total slices, to one powered grating, which eliminated a reflection for reconfiguring the focal plane. What that means is we had to align 26 slices with 26 gratings and then lay them all out nicely on the detector. But what that enables us to do, on the right, you can see our projected INFUSE resolution. We were expected to get about 3,600 spectra in a single pointing. That is about an arcsecond or two resolution for INFUSE. And just as a comparison, you can see some yellow fuse apertures in the background, looking at the Cygnus loop. So again, we get one spectra for each of those blue squares. Lets us measure that whole area instead of it was over 500,000 seconds it took FUSE to observe those 5 yellow apertures. INFUSE launched successfully on October 30th back in 2023 due to a launch delay resulting from some people being unexpectedly in the keep out zone and having to be gotten out, and then that transforming into an extensive weather balloon delay. Some gas got trapped in our detector, our payload was not on active pumping at the time, and we only observed 19.4 seconds of data. But we still got data, which was very exciting and proved that you can do FUV, integral field spectroscopy. My advisor and me, Brian Fleming, is the PI of the instrument on the top there. On the bottom is another graduate student at Colorado, Alex Houghton, and a postbac who is at Colorado. On the upper right is the X-ray region of the Cygnus loop. So for more information about INFUSE and the work that's gone on since I've left Colorado, please see Celeste's talk. You just have to hang around for another 2. So as I said, we managed to get 19.4 seconds of data. It's not the prettiest data, but we did manage to observe 3 spectral lines. It's sort of 4. The oxygen 4 line is convolved with the silicon 4 line. But even so, successful integral field spectroscopy. And I would be remiss to talk about IFU and MOS MOS and the far ultraviolet without mentioning that mirror coatings are improving. This is what has enabled INFUSE at all, and those have been advanced in many suborbital missions, as well as large format solar photon counting solar blind detectors, which let us get all of those lovely, lovely spectra. Again, many, many suborbital missions have gone into advancing these balloons, sounding rockets, CubeSats, all of it. So looking to the future, both INFUSE and OAxFORTIS have future launches. They'll continue to improve technology and develop, especially for missions like Habitable Worlds Observatory. I am currently chair of a SAG for integral field spectroscopy and multi-object spectroscopy for habitable worlds in the far ultraviolet. So if you have any questions about that, please see me after the talk, and thank you.